Yes, assalamu alaikum. So inshallah today let's continue with lecture number 2 in Thermodynamics 1. We talked last time about introduction to thermodynamics. We have defined some associated actually vocabularies related to the application of thermodynamics, the word thermodynamic itself, the term also energy and some other actually definition, and also we have introduced two dimension and unit. We have considered the three basic dimension and from which we can generate the dimension of any quantity. And also we have considered the different system of unit. We have considered the English system of unit and also the standard system of unit and the conversion unit between the different parameter between the two systems. Inshallah today we will be continue actually our talk. We said last time based on the definition of thermodynamic that thermodynamic actually is the science that deals with matter and energy and laws governing their interaction. And we said also whenever we do have a system with mass transfer or energy transfer, then we can consider this actually as a thermodynamic system, and we can apply the thermodynamic laws in terms of first and second law of thermodynamics. So let's consider today the different type of system that we can actually apply the thermodynamic laws on those systems. System actually is anything actually that you want to study. But those systems actually can be classified into two main types. The first type of system is called actually as closed system, or it may be actually called in general as system. So if it is called as system, closed system, also it is called as actually control mass. And this is actually coming from the definition of the system itself, as we will see inshallah. There is another type of system which is called also open system, or it is called actually as control volume. So it is called as open system or control volume. Now let's consider first actually the closed system. Closed system actually is actually any system that you want to study that has actually a fixed amount of mass. So the closed system is any system actually that is selected actually for a certain study with a certain amount of mass. So it has actually a fixed amount of mass, like actually this pen or something. This is actually has a rigid mass, so we don't have any mass transfer in or out. So the definition of the closed system is that it is actually a certain amount of fixed amount of mass that is selected to do a certain study. So by definition, in this case, the mass of the system is constant. So the differentiation of this constant, so it will be actually dm by dt. The differentiation of the constant should equal to 0. dm by dt actually, which means actually the rate of mass flow rate in or rate of mass flow rate out. dm by dt, which is the mass flow rate, we can consider actually m dot in equal to m dot out is equal to 0. This means actually for a closed system, the system does not allow actually for mass transfer. So in this case, mass flow rate in equal to mass flow rate out equal to 0. Mass flow rate is the rate of mass which is calculated in kilogram per second. Okay? But actually this system allows for energy transfer. So we have actually energy into the system or energy out of this system. The form of energy transfer, as we said, actually energy can transfer in the form of heat, can transfer due to temperature difference, and also it can transfer in the form of work, and it can transfer due to mass transfer. When we do have actually mass transfer, this fluid actually that is moving, it has a kinetic energy, it has potential energy, and also it may have internal energy. It should have actually internal energy. So this actually fluid has its own energy. So we do have energy transfer due to flow transfer. But in this case, a closed system is fixed amount of mass. We don't have any kind of mass transfer. So the form of energy transfer in this case to in or out of this system can be in the form of heat, which has the symbol Q. This is actually the heat, and it can transfer also in the form of work. All of this actually heat or work calculated actually in kilojoule. So the energy, the closed system allow for energy transfer in the form of heat or in the form of work. We can have actually energy transfer by heat when we do have actually only when we do have a temperature difference between two systems. So if you do have two systems with different temperature and they got in contact with each other, so in this case we can have heat transfer due to actually the temperature difference. Otherwise, actually the energy transfer is work transfer. Okay. This is in case when we do have actually a closed system. You can look at actually this closed system. It has a boundary. This boundary in most of the case actually is a real boundary. So in this case actually it's something fixed amount of mass, something that you can touch. So it has actually a real boundary. This boundary actually may be fixed or it may be moving. So let's consider this example in this slide number 13. If you look here actually you'll find we do have a closed system where we do have a gas inside the piston cylinder device, which we can actually consider as a closed system. But actually if this piston is free to move, if we are actually heating up this gas, so in this case the gas inside will be expanding. So for your knowledge, if we have free movement of the piston, so in this case the pressure should be kept constant, because the added amount of heat will try to expand the gas. Piston is free to move, so the gases will be expanded. So in this case, the pressure within the tank will be kept constant in this case. But actually, if this piston is not moving while adding the heat, so in this case, the gases will try to expand, but actually they will not be able to expand. So in this case, this heat actually will result in pressure rise within the system. So in this case, if you look at this example, we do have actually one moving boundary of the system, which is the piston in this case. So the boundary of a closed system can be fixed or moving. However, actually we don't have mass transfer. So we can consider a gas inside a piston cylinder device. We can consider this as a closed system as long as actually we don't have mass transfer to the system. We do have the other kind of system, which is actually the open system. Open system is an arbitrary region selected in a space to do a certain study. So it is called also as control volume. So control volume or open system, it is just an arbitrary region, just an imaginary region we can select in a space to do a certain study, like actually the air inside this room. So if I want actually to study the air inside this room, just I will imagine I do have imaginary boundary around this room, and then I will look at actually this room, what are crossing actually those boundaries in terms of mass transfer and in terms also of energy transfer. So the surface actually of this control volume is called as control surface. So the control surface, or it has the symbol actually CS. Control volume has the symbol CV. The control surface is the surface actually of this control volume. So as long as actually this is an imaginary boundary in most of the cases, so and it is control volume, what is fixed in this case is the volume. That's why it is called the control volume. So in this case, as it is actually an arbitrary region selected in a space, so in this case it allows actually for mass transfer. So we do have mass transfer in, mass in, and mass also, it can have mass out. And also it allows also for energy transfer. So we may have in this case energy in, and also may have energy out of this system. But in case of open systems, this energy can transfer in the form of heat, can transfer in the form of work, and it can transfer due to mass transfer. We can have energy transfer due to mass transfer, because if we do have flowing fluid inside the system, it should have actually kinetic energy, potential energy, and it should have also flow energy and also in addition to internal energy. So all of these are actually energy transfer due to mass transfer. And also may have energy transfer due to work, and we may have also energy transfer due to heat transfer. An example actually of open system, all of engineering devices or most of the engineering devices are actually steady flow device, including actually compressor, turbine, nozzle, heat exchanger. All of these actually are devices that are steady flow devices. And they are also open system, and they allow actually for mass transfer across the system. So we can consider all of the engineering devices are actually open system devices, or most of them are actually open system devices. Like in this example actually, if we look at this internal combustion engine, we burn the fuel above this piston, and the heat of combustion just press the piston to get down, and we do have a connecting rod to this piston to just convert this linear motion into an angular motion or mechanical shaft power, so that actually your car can be moving. This engine is similar to the engine in your car. So if I want actually to study this engine, we can just draw a control volume, about a control surface about or around this engine. If you look at actually this engine and look at actually what are crossing this control surface around this engine, we feed for this engine, we do have air mass flow rate, and also we do have fuel mass flow rate. which is in most of the cases we do have gasoline for internal combustion engine for car. So we do have fuel flow rate to the engine, and also we do have air flow rate. And also this fuel and air, they are burned inside the internal combustion engine, and we do have actually exhaust gases leaving the system. So we do have mass flow rate in to the system, mass flow rate of air and mass flow rate of fuel, and we do have mass leaving the system, which is actually the exhaust mass flow rate, which should equal to mass flow rate inlet, which is mass flow rate of air plus mass flow rate of fuel. If you look at actually this engine, out of this engine we do have actually a mechanical shaft power out of this engine, which has actually the crankshaft power, which is used actually to drive the car so that actually this car is moving. Part actually of this crankshaft is used actually in the radiator system for cooling the water that is used actually to cool down the internal combustion engine. So if you look at this system, we do have mass transfer, we do have mass in and mass out, so this is actually an open system. And also we do have work out of this system, we do have shaft power output of this system, which is the main output of the system, and also we do have part of this shaft power is used in the radiator system to just cool down the water, so we do have another source also of shaft power within this control surface. And based on that, actually we can apply the first and the second law of thermodynamics for this system. But this system we consider in this case, as long as we do have mass transfer, we can consider the system as an open system. There is actually a special case of a closed system, which is called actually isolated system. Isolated system is completely isolated. It does not allow actually either for mass transfer or energy transfer. So in this case, for an isolated system, we don't have mass transfer. Mass in is equal to 0, mass out is equal to 0. We don't have energy transfer, so we do have in this case the heat transfer is equal to 0, and also the work is equal to 0. We do have also one special case, which is adiabatic system. When you have actually this term is mentioned, we do have adiabatic system. Adiabatic means we don't have heat transfer. So for adiabatic system, this means actually the heat transfer only is equal to 0. However, the system may be an open system or closed system. But when it mentions, actually it is mentioned in any problem that we do have an adiabatic system. Adiabatic does not mean actually the system is open or closed or isolated. It only means that we don't have heat transfer, or the heat transfer rate is equal to 0. If we do have an isolated system, like in slide 15, if this system actually contains different subsystems inside, those different subsystems may be closed system or open system. So it depends actually which system you are studying. If you are studying actually the whole isolated system, so in this case we won't have any kind of mass transfer or energy transfer. And no need actually to apply the first or second law, because nothing is transferred from the system. But if you are studying one of the systems inside the isolated system, so in this case just draw a control surface around this system, if it is open system, and then actually look at actually the masses crossing this control surface, and actually the sources of energy crossing this control surface, then we can apply the first and second law of thermodynamics. If it is closed system, also we can also apply the first law of thermodynamics based on the closed system, as we will see later, inshallah. So it depends actually which system you are studying. This is in terms of isolated system. Type actually to study, let's move to the next slide. To study any system, we have actually to calculate the properties of the working fluid within this system. So in case of internal combustion engine, we do have the working fluid inside, we do have air plus fuel. They are actually introduced to the internal combustion engine in the form actually almost probably at the air condition, and they are burned inside the internal combustion engine, and then we do have exhaust gases under different conditions. So we need to calculate the properties of those gases while entering the system and also while leaving the system, so that we can calculate actually the amount of energy transfer across the system, and also the amount of mass transfer. Property actually is defined as any characteristic of the system, like actually the mass of the system, volume, energy of the system, pressure, temperature. All of these are actually properties of the system. But actually the properties are divided actually into two types. Properties, we do have two types of properties. We do have what's called actually extensive properties, and we do have actually what's called intensive properties. Extensive properties, those are actually does not depending on mass, so they are not actually function of function of mass. Extensive properties are function of mass. Intensive properties are not function of mass. Like what? Like extensive property, like the mass of the system, like the volume of the system, and total energy of the system. Those are actually extensive properties. They are depending actually on the size of the system itself. And intensive properties, those are the properties that are independent of mass, like temperature, pressure of the system, and also all of the specific properties. All the specific properties are actually independent of mass. Specific properties are the properties actually per unit mass, like a specific volume. So specific volume is actually defined as the volume per unit mass calculated in meter cube per kilogram, and it is equal to actually 1 over density. So the specific volume equal to 1 over density. Also, like the energy, specific energy is equal to the total energy divided by the unit mass, which is calculated usually in kilojoule per kilogram. Also, we do have another specific property, another very important specific property, which is actually called as the specific gravity. You will introduce to actually specific gravity in the next slide, inshallah. The properties, as we said, extensive properties and intensive properties. Extensive properties are mainly function of mass, or depend on the size of the system, and the intensive property are actually independent of mass. So actually all specific properties, which are the properties per unit mass, are intensive properties in addition to temperature and pressure. But let's try to understand actually the main difference between extensive and intensive property. Let's consider a system, and let's divide actually this system into subsystems. So let's say system number 1, system number 2, 3, 4, 5, 6. So in this case, for the extensive property, when I want actually to calculate the mass of the whole system, so it should equal to actually to the summation of the masses of all subsystems. Like this, also the volume. If I need to calculate the volume, so it should equal to the summation of all volume actually of all of the subsystems. But in case of intensive property, if I need actually to calculate the pressure, it should equal to actually the pressure of any subsystem, because the pressure should be actually similar to the pressure to the other point. And if it is different, it should be actually slight differences, and it should be actually depending on the distribution of the pressure within the system. But actually, we cannot say the pressure of the whole system is equal to the summation of the pressure of the subsystem. No, pressure is equal to only the pressure of one subsystem, or equal to the average pressure of the system. And also like this, we can say the temperature equal to the temperature of any of the subsystem. But in case actually of extensive property, which depend actually on the volume or the mass of the system, in this case the property should equal to the summation of the property of all of the subsystem. This regarding actually the properties. If we move to the next slide, which is a continuum, to study actually any system, this system should be representing actually a continuum. What's it called? A continuum system. Continuum means actually a homogeneous system without holes or separation between between the working fluid, between the molecules of the working fluid within the system. So let's say I want to study the air inside this room. So in this case, actually, let's say I want to calculate the pressure or measure the pressure within this room. So actually, we can come at the center of this room, and then we can measure the value of the pressure, and this should be the average value of the pressure of the system. But if this room actually contains some hole or some vacuum point inside this room, so this means actually if I measure the pressure at some point, this is actually not representing actually the pressure for the whole room, because it contains some holes or some vacuum point in this case. So this room in this case does not represent actually a homogeneous system, or does not represent what's called actually a continuum, and in this case we cannot measure the properties of the system. So to study any thermodynamic system, this system should represent what's called a continuum, and it should represent actually a homogeneous system without any holes or separation between the molecules. As we said, all specific properties are intensive property. We talk about actually the density and the specific volume, and the specific volume is equal to 1 over density. And we do have actually another very important specific property, which is called actually the specific gravity. So a specific gravity S of any substance is equal to actually the specific weight gamma of this substance divided by the specific heat actually of water under standard condition at temperature equal to 4 degrees C. We say the specific heat is equal to rho g, so the specific gravity of any substance will equal to rho g of this substance. Rho is the density multiplied by g, which is gravitational acceleration of this substance, divided by rho water multiplied by gravitational acceleration. So g will go with g. So in this case, actually, we can define actually the specific gravity of any substance as the density of this substance divided by the density of water under a standard condition. Usually, in most of the problem, we do have this density of water is equal to 10 to the power 3 kilogram per meter cube. So the density of water under a standard condition, under atmospheric pressure of liquid water, if it is not given, we can consider this value 10 to the power 3 kilogram per meter cube. If you look at actually the table in this slide, slide number 18, you will see actually the value of a specific gravity of different fluid, starting with water. The specific gravity of water will be the density of water divided by the density of water, and it should equal to 1 in this case. And then we do have the specific gravity of some other substance, including blood, seawater, gasoline, and some other actually quantities. Here actually in this slide also, in this black box, you will find we do have a simple example. If we do have a system with a volume equal to 12 meter cube and mass equal to 3 kilograms, and in this case we can calculate the density, which is equal to the mass divided by the volume, so it will be 3 over 12, which is around 0.25 kilogram per meter cube. And actually you can calculate the specific volume, which is equal to 1 over density, which is the volume divided by mass, which should equal to 4 meter cube per kilogram. So all the properties again are extensive, either extensive depending on mass, or intensive, they are actually independent of mass. Right, to study actually, let's move to the next slide. To study any thermodynamic system, thermodynamic actually deals only with equilibrium state. So to study any thermodynamic system, this thermodynamic system should be at equilibrium state. Equilibrium means actually a state of balance in which we don't have any kind of driving force or driving potential through the system. To have actually the system under equilibrium, we should have actually different kind of equilibrium that should be achieved in this case. We should have this system under thermal equilibrium. Thermal equilibrium means actually the temperature within the system at any point should be the same. This means actually temperature distribution is uniform. Temperature is the same everywhere. So this is the meaning actually of thermal equilibrium. And also to have the overall equilibrium, we have to have mechanical equilibrium, which means the pressure within the system should be the same everywhere. Also, we should have phase equilibrium. We should not have actually any phase change. The substance should be presenting either actually a single or double phase, but actually we should not have actually any change from one phase to another. Like if we do have actually boiling water or something, so in this case part of the water while boiling at 100 degrees C, let's say at atmospheric pressure, water will boil at 100 degrees C. So while heat is added at 100 degrees C, the temperature will not be raising, but actually this heat will be used to convert the liquid into vapor. So in this case we do have a phase changing process, so we cannot apply actually the thermodynamic law when we do have actually a transition of phase. So it should be actually representing a phase equilibrium. We don't have actually any kind of phase change, and also to have the overall equilibrium we should have a kind of chemical equilibrium. We should not have actually a change actually of a species from one species to another, like if we do have combustion or something. Burning actually of fuel, hydrocarbon fuel, should result in carbon dioxide and also result in H2O. Burning using air, and it should result actually in this case, if we are burning using air, it will result also in N2, nitrogen, and also some NO and NO2 emission. So in this case only CH4 plus air, which is O2 plus nitrogen, can be converted. If we do have chemical reaction, it can be converted to some other different substance. We do have carbon dioxide, H2O, and some other actually substance. So if we do have chemical reaction, so in this case the system in this case is not at chemical equilibrium. So to study any thermodynamic system, the system should be representing, should be at the equilibrium state. And to be at the equilibrium state, we should have thermal equilibrium, we should have mechanical equilibrium, and also we should not have phase change. We do have phase equilibrium, and also we should not have actually any chemical reaction, which means we do have a chemical equilibrium also. This is the meaning of equilibrium. We do have another important definition which is called the state postulate. A state postulate is defined as actually the number of required properties to specify a state of a substance. So let's look at slide 20. So in this case we do have nitrogen. To specify actually the state of this nitrogen, we have to provide two independent and intensive properties. So in this case, a state postulate is defined as actually the number of required properties to specify a state of a system, and actually to specify a state of a system we have to have two independent and intensive properties. Again, to specify a state of a system we have to have two independent and intensive properties. Intensive properties, not extensive properties. So to specify the state of this nitrogen, we can define the temperature, and also can define a specific volume. We may define actually the pressure and the specific volume, any two independent and intensive properties. Then we can calculate actually from those two properties, we can calculate the properties of the other properties of nitrogen or of the system. We do have one special case when we do have actually a phase exchange process, like if we do have water boiling. So in this case actually we cannot consider pressure and temperature as two independent and intensive property, because we know all actually water at atmospheric pressure should boil actually at 100 degrees C. So if you look at actually the series of state when this water is boiling from the liquid state until actually it is fully converted to the vapor state, in this case actually all of this state while the conversion process has the same pressure and same temperature. So in this case pressure and temperature are not actually, while the phase exchange process are not independent, because actually they are the same. All of the point or all of the states here have the same pressure and same temperature. So we cannot say actually this pressure and temperature are an independent and intensive property. So in this case we have to have two different properties to specify the state of some substance, while actually the phase exchange from the liquid phase to the vapor phase. Let's move to the next slide and let's define the differences between cycle and process, and let's also introduce a different type of processes. Process actually is defined as a change from one initial equilibrium state to another state. So process is defined as a change from one initial state, the first state, to a final state. Like if we do have a gas in a piston cylinder device, let's say this is state number 1. We do have the pressure inside this piston cylinder device. Pressure of this gas is B1 and the volume is V1. And let's represent this process on the PV diagram. So let's say this is actually state number 1 with pressure B1 and we do have volume V1. So if we actually compress this gas, just press this piston to inside, and this piston has moved to this position number 2. So in this case the volume of the gas has been changed, it has been reduced. We do have V2 is less than V1. But what will happen to the pressure in this case? The pressure will be increasing. So in this case we do have B2 is greater than B1. So let's represent this in the system, the compression process. We have to move actually in this direction. So the process has been proceeded in this direction, in the direction of the reduction of volume and the increase of pressure until it can reach actually state number 2, where we do have V2 is less than V1 and B2 is greater than B1. This is actually a kind of general real process. There is another special kind of process which is called actually quasi-static or quasi-equilibrium process. This quasi-static or quasi-equilibrium process assume actually the process is done very, very slowly, so that actually equilibrium is attained actually at each intermediate state from the initial state to the final state. So while this piston is moving, so actually we should have actually equilibrium is attained actually everywhere while this piston is moving, which is not actually real. So if you are moving this piston due to the friction, you will find actually here friction between the gas and the piston. You will find actually beside this piston the temperature may be a little high, actually higher than the temperature at the end of the cylinder. So as the temperature is different, so we don't have thermal equilibrium, and also like this the pressure should be different. While actually moving the system, the pressure will not be the same within the system. So this means actually we don't have equilibrium. But in a quasi-static process or quasi-equilibrium process, we assume actually equilibrium is attained actually while this piston is moving, or while actually the process is proceeding from the initial state to the final state. So this is actually a kind of imaginary. Let's move to another topic, which is actually the temperature and temperature scales, or temperature measurement. Actually, temperature measurement is based on what's called the zero slope thermodynamic, and the zero slope thermodynamic states actually if we do have two systems that are actually in thermal equilibrium with a third system, this means actually the two systems are also in thermal equilibrium. What is the meaning of that? So it says actually if we do have a kind of two systems, let's say system number 1 and system number 2, both of those systems are actually in thermal equilibrium with the third system. Thermal equilibrium, this means T1 is the same as T3, and the second system is in thermal equilibrium with this third system, so T2 is the same as T3. So based on that, actually we can say actually that the thermal equilibrium, the system number 1 and system number 2, they are also in thermal equilibrium, however they are not actually in contact with each other. So if we do have two systems that are in thermal equilibrium with a third body, so this means actually the two systems are in thermal equilibrium, however actually those two systems are not in direct contact with each other. What is the meaning of this? The meaning of this zero slope thermodynamics that actually this third body is the temperature measuring device, which is a thermocouple. This means if I do have a thermocouple or any other actually temperature measuring device, if we do have this device, is it just inserted within one system, and it has the same reading for another system, this means actually we do have the same temperature of the two systems, and this means actually the two systems are in thermal equilibrium, however they are not in contact with each other. The simplest actually case of temperature measuring device is actually the liquid in glass thermometer. Inside this liquid in glass thermometer we do have a kind of liquid which is sensitive to heat transfer, like mercury or something. Mercury has the symbol Hg. So if we want actually to measure a temperature of a medium, just insert it inside this medium. So this mercury actually will be expanding, and that actually at a certain position it will be stopping. We do have actually a scale here outside actually this temperature measuring device, and based on this case actually on this scale we can calculate, we can measure, or we can read out the temperature, and this is actually is called the scale. So what are actually the temperature scales, and based on what actually we have done those scales? So we do have different temperature scales. So temperature scales, we do have what's called the Celsius scale, which is used actually in the SI system of unit, and we do have the Fahrenheit scale, which is used actually in the English system of unit, and we do have another scale which is the absolute scale, or it is called actually the thermodynamic absolute temperature scale. What are the difference between actually those three scales? So to have actually any scale, you can make your own scale. But actually to have any scale, you have to have actually reference points. So for the Celsius scale, they said actually we'll take two reference points for water. The ice point of water, which is the point, the temperature of a mixture of water, which is called the triple point, which is actually a mixture of water plus ice plus actually water vapor. So the temperature of this mixture, we call it actually the ice point. So at atmospheric pressure, at pressure equal to 1 atmosphere under atmospheric condition, we do have actually the ice, the temperature of ice mixture. We consider actually this temperature to be equal to actually 0 degrees Celsius. And we do have actually the steam point, the temperature of boiling water, or T steam or steam point. We will consider actually the water is boiling at temperature equal to 100 degrees C. So based on that, we can actually calibrate this device. We can calibrate this device to have actually a reading of 0 when the temperature actually, when we do have ice mixture, and to have actually a reading equal to 100 degrees C when we do have actually a water that is boiling, which is called actually the ice point. And in between, or actually below or above, we can actually make the scale or calibrate the scale to read actually the other actually temperature of different system at different temperature condition. So to have any scale, we have to have actually a reference point. So in case of Celsius scales, you have selected the ice point, which is a triple point of water, in which actually we do have a mixture of liquid water plus some ice plus some water vapor. They are existing in a mixture. The temperature of this mixture, we consider it actually 0 degrees Celsius. For steam, we consider actually boiling point equal to 100 degrees C, and based on that we can make this scale to read actually the temperature of any other system. Fahrenheit scale, I think they consider actually a mixture of like ammonia, and they came actually with another scale. This is actually used in the English system of unit. But if you use actually the Fahrenheit scale to measure the ice point, you will find actually the temperature of the ice 0 degrees Celsius. When the reading equal to 0 degrees Celsius, the temperature using the Fahrenheit scale will equal to actually 32 degrees Fahrenheit. And when the temperature equal to 100 degrees C, so 100 degrees C is equal to 212 degrees Fahrenheit. And based on that actually, we can get the relation between the scale of Celsius and Fahrenheit scale, that the temperature in degree Fahrenheit is equal to 1.8 multiplied by the temperature in degree C plus 32. And this is the relation between the degree Fahrenheit and the degree Celsius scale. Okay? This is in terms of Celsius and Fahrenheit scale. We do have another scale which is called the absolute scale or the thermodynamic temperature scale. This scale actually is not related to the property of any actually fluid or ammonia in case of Fahrenheit, and in case of water in case of we do have actually the Celsius scale. It depends actually on the absolute pressure, on the absolute vacuum pressure. So for the thermodynamic temperature scale, for this scale actually it considers actually the temperature is equal to 0 Kelvin when the pressure, the absolute pressure is equal to 0. We cannot actually in our nature, we cannot have pressure less than absolute pressure equal to 0. Actually atmospheric pressure is equal to 10 to the power 5 Pascal. This is actually the pressure that we are living in. But the absolute vacuum pressure means actually the pressure is equal to 0. We call the pressure as vacuum when it is less than atmospheric pressure. But when we do have absolute vacuum, this means actually the pressure is equal to what? Pressure is equal to 0. And in this case, the reference temperature will equal to 0 in this case. Type to calculate actually this temperature in degree C or something, they came up actually with a gas. They put this gas inside actually a rigid tank, so the volume of this tank is fixed, and they have connected here a vacuum pump just to suck this air actually to reduce the pressure. So we'll be reducing the pressure, and each time we'll be calculating the temperature in degree C. And we can plot actually this relation between pressure and the temperature in degrees Celsius. So each time actually when we have a pressure, we can record the temperature, reduce the pressure, and then again actually reduce the temperature, read the temperature, until actually we reach the value of absolute vacuum, when B absolute is equal to 0. In this case, the temperature should equal to 0 Kelvin, and they have found actually this temperature on the Celsius scale is equal to minus 273.15 degrees Celsius. And based on that, actually we can get the relation between the Kelvin scale, that the temperature in Kelvin, we don't have degree here, because this is actually not degree, this is actually the absolute temperature. So the temperature, the absolute temperature in Kelvin is equal to the temperature in degrees Celsius plus 273 plus 0.15. And this is the relation between the Kelvin scale and the Celsius scale. This Kelvin scale is used actually in the standard system of unit, and we do have another scale which is Rankine scale. You can actually, this is actually for the English system of units. The absolute temperature is called Rankine, and the relation between the Rankine scale and the Kelvin scale, we can get it actually by substituting all of these relations, the relation between temperature in Fahrenheit and degree C, and temperature between actually Kelvin and degree C. Then we can get the relation of temperature in Rankine. It should equal to actually 1.8 multiplied by the temperature in Kelvin. Okay, and those are actually all the relation or for temperature measurements. So this is actually one relation between degree C and degree Fahrenheit, and then between degree C and degree Kelvin, and then between Rankine and Kelvin. And for the English system of unit, we do have also another relation between Rankine and degree Fahrenheit. Let's look here in the next slide, slide 26. We'll see here in those two actually thermometer. We do have when the temperature is equal to -27 in the left hand side one, -27 3.15, the temperature in Kelvin is 0. If we use actually the Fahrenheit scale to read this temperature when the absolute vacuum is equal to 0, the temperature will equal to -459.67. This actually temperature will be in degree Fahrenheit, and it should equal to 0 Rankine. And based on that, we can get the relation between Rankine and the Fahrenheit. The temperature, it is written here, temperature in Rankine will equal to the temperature in degree Fahrenheit plus this number, which is 459.67. Okay, this is actually the final relation between Rankine and degree Fahrenheit. And based on that, actually, we can conclude with this, that we do have the temperature difference, delta T, when we do have a change. Let's say we do have a process or a change from, let's say, state number 1 toward the state number 2. So the temperature in Kelvin, T1 equal to T1 in Celsius plus 273. T2 in Kelvin equal to T2 in Celsius plus 273. If we just subtract the two equations, so we'll see actually delta T in Kelvin is the same as delta T in degree Celsius, because just we do have addition here, it will disappear. And also we do have delta T in Rankine is the same as delta T in degree Fahrenheit, and we do have delta T in Rankine from Rankine and Kelvin relation equal to 1.8 delta T in Kelvin in this case. And also, yes, so those are actually the three relations for temperature difference when we do have a system undergo a process from 1 to 2. So delta T in Kelvin should be the same as delta T in Celsius, and same also for Rankine and Fahrenheit. But from English system to the standard system, we connect delta T of Rankine equal to 1.8 delta T in Kelvin, and also delta T in Fahrenheit is equal to 1.8 delta T in Celsius. In the next slide, we do have simple example. We do have during a heating process, the temperature of a system rises by 10 degrees C. Temperature rise 10 degrees, so this means delta T in degree C is 10. And we need to calculate the temperature rise in Kelvin, Fahrenheit, and Rankine. Based on that, we can calculate this. In Kelvin will be the same as temperature rise in degree C. Temperature rise in Rankine will equal to 1.8 multiplied by delta T in Kelvin. And this is actually a very simple example. Delta T in Fahrenheit will be the same as actually delta T in Rankine. Okay? So we'll continue inshallah our talk next time. We'll consider our talk actually to be on pressure. We'll consider pressure and pressure scale to end up actually with this chapter number 1. Thank you.